All right, so in this video, we're going to take a look at some examples here where we actually set up the triple integral three different ways. We're going to set up the triple integral to compute in rectangular, cylindrical, and spherical. So the problem that we're going to look at is where T is a solid. Remember, this is our T, solid closed bounded region, in the first octant, bounded by this sphere and the coordinate axes. So if I can draw this, if we've got our XYZ space, then in that first octant, it's going to be this part right here, where we now have what looks to be just a part of a ball. Remember, it's just above the XY plane in that first quadrant of the XY plane. So that's what we're looking at. The trace down into R2, which will come into play, would just be the part here, again, in the XY plane with a radius of 2. All right, so to get this thing set up, like I said, we're going to do it three different ways. We're going to go rectangular, we're going to go cylindrical, and we're going to go spherical. So rectangular is going to start where we're allowed to keep our X, Y, and Z as they are. So we'll do an X, a Y, and a Z. And then in terms of dV, that's going to be some combination of dz, dy, dx, or dx, dy, dz, or whatever. And in this particular problem, I think it's just as easy to go dz, dy, dx. So if we go that route, this is going to be z equals and z equals. We'll have a y equals and a y equals on the second one, and then an x on the last one. So for z, we're going to focus on this picture. The top part, if you will be the sphere. So if I solve that for z, I'm going to get z equals the square root of 4 minus x squared minus y squared. We're bounded below by the coordinate axes, so that's going to be where z equals 0. So we'll put a 0 there. So that's going to be the top, and that's going to be the bottom from this picture here. Now we're focusing on x's and y's, so we can focus on this picture alone. So if we focus on this picture going with respect to y, then this vertical bar would be up here, giving us our top part of y equals root 4 minus x squared. If we let z equal 0, then if I solve that for my y, I get this guy right here. So the bottom would be 0, the top would be the square root of 4 minus x squared. And then the x's would range, of course, from 0 over to 2. 0 to 2. So there would be your setup in rectangular coordinates. Now, in cylindrical coordinates, we'll also have that triple integral, but we can't have x's, y's, and z's. We can have r thetas and z's. So our x is going to be r cosine theta, the y is going to be r sine theta, the z is going to be z, and then the dv is going to be the r dz, dr, d theta. Now, if this is the route we choose to go, that would mean that this would need to be z equals, this would need to be r equals, and this would be theta. Now remember, the z here is the same z as right here. So we'll be able to start here at 0, but I can't put in this quantity for this. Since we're r thetas and z's, I can't have x's and y's. But much like you saw in a previous example, this is going to be 4 minus r squared right here. So now we're going to be okay in moving forward. Now, with r's and thetas, I'll come back to this picture. My r value is going to range from here out to here, so a distance of 2. So 0 to 2. And then the theta, as it sweeps from here around, would be 0 to pi over 2. And so there's your setup for cylindrical. Now for spherical, we'll have our triple integral. And much like cylindrical, we are going to have to substitute stuff in here. So the x is going to be rho sine phi cosine theta. The y is going to be rho sine phi sine theta. The z is going to be rho cosine phi. And then the dv is going to be rho squared sine phi d rho d phi d theta. So it's kind of a mess, but we're not evaluating, so it's okay. So there's the x, there's the y, there's the z, and then the rho squared sine phi d rho d phi d theta is going to be your dv. All right, so we've got our rho equaling something there and there. We've got our phi there and there, and we've got our theta there and there. So for the rho, that's going to be from here coming out, and so that's going to be a distance of 0 to 2 as well. And I know it's 0 to 2 because this has a radius of 2, so from there out. The phi, remember, starts right here and it drops down. So it will start here at 0, and for us to get down on the xy plane, we're going to drop down pi over 2. So 0 to pi over 2. And then finally, the theta that you saw here will be the same theta that you see here. Therefore, that's going to be 0 to pi over 2. So a good example on how, given a certain problem, the 3 different coordinate systems we've discussed so far will allow you to set up and evaluate however necessary. All right, so this problem is going to be very similar to the last one in the sense that we're going to set it up in 3 different ways: rectangular coordinate system, cylindrical, and spherical. So T is going to be the region bounded above by the sphere and below by the plane z equals 1. So our picture is going to look something like this, where we have our sphere right here, but then we have our plane z equals 1. So the actual volume that we're computing is going to be this right here. So to get things started, we'll take a look at rectangular, and we know we'll have our triple integral. And since it's volume, there's not going to be a function there. It's just going to be the dv, which for us, in rectangular, I'm going to go dz, dy, dx. So we'll have z's, we'll have y's, and we'll have x's. Now, to get things started with the z, we'll have our top part here and our bottom part here. The top would be the sphere, the bottom would be the plane. So the bottom would be that 1, and then that top would be the root 4 minus x squared minus y squared when solving this for z. Now, once we take this and go back into R2, we're going to need to figure out what the trace is going to be in R2 on the xy plane. And so you can see this is z equals 1. So if I let z equals 1 right there, subtract that over, that's going to give me x squared plus y squared equals 3. So that's what we're going to be studying now in the xy plane. So in terms of the y's, if we look at this vertically here, you can see that since z is equal to 0, and we go ahead and we can solve this, we would get y equals the square root of 3 minus x squared. On the bottom, we'd get the negative square root 3 minus x squared. So square root 3 minus x squared, and then I didn't quite leave enough room for this. You think I would learn by now. Negative root 3 minus x squared. And then for the x's, of course, that's going to range from here over to here. So negative root 3 to positive root 3. So there would be your rectangular setup. Now for cylindrical, once again, triple integral, the dv is only going to be the r, dz, dr, d theta. Now the z's, seeing as they're the same z's from above, we would have our 1, and then just like the last example, we'd have this root 4 minus r squared right here. So we have a 1 and then a root 4 minus r squared. For the r and the r is going to start here and move out a distance of square root of 3. So if I move that out, that's going to be 0 to root 3. And then our theta is going to go from 0 to 2 pi. 0 to 2 pi because it's going to go all the way around. So cylindrical is pretty straightforward, especially once we get through the rectangular one. So let me go ahead and move this up a little bit. And then for spherical, we're going to have our dv being the rho squared sine phi, d rho, d phi, d theta. So our rho, our phi, and our theta. So this is one where we're going to have to think a little bit. I'll go ahead. The theta is going to be pretty obvious. Not only is it from up here, but you can see the theta is going to go all the way around. So I'm just going to mark that as 0 to 2 pi right now. But the other parts we're going to have to think about a little bit. For example, the rho. If we take a look at this rho, that's going to come out. Well, what we're really going to be studying now is going to be this from here up to here. So it's just going to be this part. So my top number is going to be what this is. My bottom number is going to be what this is. The top isn't too hard. You can see that rho squared would equal 4. Therefore, rho would equal 2. So the top part, rho equals 2, isn't too bad. For that bottom part where we have z equals 1, well, we know that z equals rho cosine phi. Therefore, the rho would equal secant of phi. So this bottom part right here, that would be secant of phi. So I'm going to drop that in right here. So secant of phi. Now, the only part we have left would actually be to figure out the phi. That's going to be from here dropping down. So from here, that's going to start at 0. So I'll put a 0 there. And then this is going to drop down until you have this intersection right here. So we've got 0 starting here, and then it's going to have to drop down to whatever this is. Much like an earlier example, to figure that out, we can set some things equal to each other. Fortunately, this one's not too bad. I can simply take from here, I can say that since my rho is 2, 2 equals secant of phi, which means that cosine of phi equals 1/2, and that phi would equal pi over 3. So again, that 2 right there came from this 2 right here, which came from this up here. So if I take these two things equal and solve it, that's going to give me my pi over 3. So from 0 down to pi over 3. So I'll punch the pi over 3 in there. And there we have a setup. So you'll notice, again, all three of these will give you the same exact answer if you evaluate. They all serve different purposes, though, given the context.